This diagram illustrates a classic puzzle in computer science. You look out your window and see your lawn is completely soaked. Two immediate causes come to mind. It rained overnight, or your automatic sprinkler system turned on. But these two events are interconnected. If it rained heavily, a smart sprinkler system likely sensed the moisture and kept itself powered off. To calculate these overlapping probabilities, artificial intelligence relies on this structure, a Bayesian network. Specifically, it maps the problem using a directed acyclic graph. The rules here are straightforward. The nodes represent our variables: rain, sprinkler, and wet grass. The directional arrows define dependencies, creating clear cause and effect relationships between parent and child events. By forcing messy real-world scenarios into this strict visual hierarchy, an AI can isolate interconnected causes and calculate their probabilities without getting trapped in circular logic. This table provides the starting data we need for our first objective, calculating a specific joint probability. We are going to find the exact likelihood that it is raining, the sprinkler is off, and the grass is wet. We solve this using the chain rule of probability, which multiplies the conditional probabilities of each node given its parents. We take our baseline 20% chance of rain and our 80% chance of wet grass given those exact weather conditions. Notice the missing variable. Our given data only tells us there is a 1% chance the sprinkler turns on during rain. We derive the chance of it staying off by subtracting that 1% from 100%. This leaves us with a 0.99 probability. Multiplying our three values together yields 0.1584, giving a 15.84% probability for this specific scenario. The chain rule allows the AI to step straight down the graph, mapping out the mathematical likelihood of one highly specific sequence of events from many possible outcomes. Next, we calculate the marginal probability, the overall likelihood of a single node being true, regardless of the rest of the network. For our root node, rain, there is no math required. It stands alone with its prior probability of 20%. Moving down to the sprinkler node requires the law of total probability. Because its state depends on the weather, we must calculate its odds across both possible states of its parent, when it is raining and when it is not. We multiply the 1% chance the sprinkler runs during rain by the 20% chance of rain, and add that to the 40% chance it runs on a dry day, multiplied by the 80% chance of dry weather. The overall marginal probability of the sprinkler turning on is 32.2%. Now look at the wet grass node. It is influenced by two parents, rain and sprinkler. This means there are four distinct causal pathways that could result in a soaked yard. Grab a notebook and pause the video right here. Write out all four true and false combinations of those two parent nodes. Calculate their joint probabilities, multiply each by the chance of wet grass, and see if you can arrive at the final overall percentage. Let's review the steps. First, we map the scenarios where the sprinkler is running. We calculate the probability of the sprinkler being on while it's raining and the sprinkler being on while it's dry, multiplying each result by the likelihood of wet grass from our data table. Then we map the scenarios where the sprinkler is off. We calculate the odds of it remaining off during rain and off during dry weather, again multiplying those numbers by the probability of the grass getting wet in those specific conditions. With all four independent pathways calculated, we simply sum the results. The final marginal probability of waking up to wet grass is exactly 44.838%. By tracking every single possible combination of events, the AI ensures its final probability is mathematically exhaustive, completely eliminating blind spots. This completed summary chart maps our final derived percentages next to the foundational graph. We use the chain rule to trace specific single paths and the law of total probability to sum up overall outcomes across branching paths. Keep this visual framework handy. Use this exact mapping technique and calculation structure when working through your continuous assessments. Real-world data is full of overlapping dependencies. Breaking these environments into structured parent-child graphs allows us to translate messy uncertainty into precise, computable logic.